Welcome back to Beyond the Patterns. So I haven't been recording videos for quite some time now, but I really wanted to go ahead and really show you some of the things that we've been doing in the past. In particular, we had really interesting visitors from all across the globe virtually in our lab, and I would continue to highlight their presentations in this lecture series. And one of the best presentations in the past year was actually given by Robert Sablatnig. So he is a professor at the TU Vienna, and he is actually born in Klagenfurt in Austria in 1965. Then he was from 92 to 2003 assistant professor, and from 2003 to 2010 associate professor of computer vision at the pattern recognition and image processing group at the TU Vienna. Then from 2005 and 2017, he was the head of the Institute of Computer-Aided Automation. And since 2010, he is heading the Computer Vision Lab, which is part of the 2018 founded Institute of Visual Computing and Human-Centered Technology, which he is heading since 2019. His research interests are 3D computer vision, including rangefinder, stereo vision, shape from X, registration, calibration, robot vision, machine and deep learning for computer vision, video data analysis, automated document analysis, and multispectral images, as well as virtual and augmented reality and applications. And in particular, he has really awesome contributions in cultural heritage preservation. And we've been meeting for a long time in the time machine context, so we've been also working in this project together. And I'm really glad that we had him here as an invited speaker. And now I'm able to present his talk that he was giving here, which was entitled MultiSpectral Imaging and Writer Identification for Historical Manuscripts. Robert, it's a great pleasure that you've been here, and now the stage is yours.
Thank you for this nice introduction, and of course also for giving me the possibility to talk a little bit about things we do here at the Computer Vision Lab. And yeah, today we're going to hear something about multispectral imaging and writer identification. I hope it works now. So maybe a short introduction what the Computer Vision Lab is. So we are a group of about 35 people working in computer vision, as the name says, and especially in the area of 3D vision, document analysis, machine and deep learning, of course, and motion tracking. And we have also a couple of applications we are working on, mainly medical image processing, industrial vision, cultural heritage, where you will hear more today, surveillance and embedded assisted living. So these are the people here. We have about 35 people, 4 of which are postdocs and 4 faculty assistants here, 3 professors, and a lot of pre-doc master students. And you see the blue ones here are faculty of the university. The rest is on soft money. That means we also have a couple of projects always running. Currently, it's about 20 projects. Some of them are sponsored by the EU, some of them of the local research funding agencies. And there's also some projects with the ministries and federal police, for instance. We have about an annual turnover of 2 million euros. And about 22 full-time equivalents of people that are producing a couple of papers per year. And approximately 10 master theses are finished and 1 or 2 PhD theses per year here at this group. Now, today we're going to focus a little bit on the document analysis, where we do almost everything that is concerned with document analysis. However, we start with imaging, and here multispectral imaging, and maybe this is also kind of interesting to you. And then I selected the writer recognition identification as one of the topics. Of course, we do also OCR, HDR, layout analysis, and other things. Now, what can you expect? Now, in the first part, we will hear a little bit about multispectral imaging and why we think that multispectral imaging is important in the area of cultural heritage, how the image acquisition is done and what can be improved, because most of the people do not care about image acquisition in this area. However, for getting good results, it's necessary to think also about the image acquisition, especially in multispectral imaging. And then we see what we can do with the data acquired and what can be done for the ones that need this data, especially for the humanists that actually then use this information for their research. And to see that this right identification is not only for historical manuscripts, we're going to have a little excursion also into forensics and police work and see how the whole work can also be used more or less. Now, why multispectral imaging? What is important or what is different from the conventional photographic imaging? Usually if you make an image with a camera, you just want to reproduce the appearance of an object. It means you would like to have the same image as you see it with your eyes, and this is why it was for the last 150 years just tailored to the human eye, and that's why we see images like in everyday images perfectly arranged for our human perception. However, there's more. So usually in imaging, there's more to see, and multispectral imaging is also working in the infrared, in the ultraviolet part, which cannot be seen by the human eye. And then you make things visible that are usually hidden to humans so far. However, this multispectral imaging is more than just giving extra channels. So it's not just RGB and plus something else. It is more, because here we don't focus on this human vision. And as you know, we have these cones there with 3 different wavebands and get our color perception. But we are more focusing on real frequencies. And here, the human vision, as you see, you have this short, medium, and long wavelengths. And you see these medium and long wavelengths have a large overlap, whereas these short and medium have not so much overlap. Well, this is because we learned how we look over the last millions of years, and it turned out that maybe this is the best way. And we have these 3 cones there, different ones for red, green, and blue, as we name them. And these are the primary colors. However, this is really specific to humans. So other animals have different visual systems. And in addition, we do not care much about spectra or so, but we just see images. However, if you want to really get all the information that is in one object, you have to care about spectra. And this is a mix of wavelengths, and some of these wavelengths are getting into the camera and some are not getting into the camera. And the idea is to find out which are arriving at the camera, and not just as a mix of wavelengths, but we would like to separate these wavelengths from each other. So usually, as you know, you have some kind of illumination with some kind of spectrum here. It reaches a surface point where the part of the spectrum gets reflected, and here the reflected spectrum is hitting, for instance, the eye, and then you have these 3 stimuli on the cones, and you get more or less 3 different values, one for blue, one for green, one for red. And then you perceive the color, let's say yellow, because yellow, you don't have any yellow sensors, but with mixing these frequencies, you get the yellow impression. And more or less, you can say this is a psychological phenomenon, and maybe other humans or other animals see it different. So maybe your yellow is not the same yellow as for someone else. So this is kind of very, very person-related or related to the vision. However, what is also very interesting is about this kind of mixing of frequencies. Why? Because in principle, you would have a yellow ball, and this yellow ball, as you see here, as a spectrum, has a very narrow spectrum. So you just have this yellow part here. However, if you take your eyes, you don't have yellow receptors, so you get the mix between these short, medium, and long band frequencies, and you get this mix, as we have seen before, between these 3 different things. If you look at a computer screen, as you do it now, for instance, there is no yellow there. So it's also a mix between these kind of blue, red, and green values, because it was really made for the human visual system, such that it's easier for you to get immediately these kind of frequencies, and you see this yellow. However, as you see, this is no longer really a single frequency, but it's a mixed frequency, because you have three different sensors there. However, what we would like to have is, as already said, in multispectral imaging, if possible, some really narrow band frequency, in order to get the other frequencies out of the whole thing. Why? We will see in a minute. For the human visual system, it doesn't really matter how or not much matter how the illumination, or which kind of spectrum the illumination is there, because if you have different spectra, we get more or less the same color sensation, because we're used to adapt ourselves to different illumination. It goes up to a certain point. Of course, if we have reddish spectrum, then of course we see it reddish. Otherwise, it doesn't really matter if you have daylight or incandescent light or halogen light or white LEDs. You more or less get the same impression of the colors, because your brain is somehow correcting for the missing frequencies. It is adjusting for the color impression. For getting the information, however, of an object, like you see here, a manuscript, it's necessary to get more than the frequencies that hit the eye, and that's why we extend this range to infrared and ultraviolet in order to get more information. And of course, also what we would like to have is separation between the different frequencies or colors also in the image. Why infrared? Infrared has been used a long time, especially in the area of art and getting the underdrawings there. Van Asperen de Boer, for instance, was one of the first who discovered that colors, paint colors, are transparent. So some colors get transparent, and the good thing is then the infrared rays get through the colors and are reflected in the background, and then you can kind of get the information that is hidden behind the painting. As you see here, there's some line here, there's something here, and this is what is called underdrawing. This underdrawing is more or less the sketch that artists use to produce their painting. So there is more information, and it's even very interesting that you can look underneath, for instance, inks. If there was ink spoiled over the document, that you can afterwards read the whole text as if there was no covering ink on that. And this is how it works, because we have different frequencies. If you have X-rays, for instance, they would go through everything. But still, part of the X-rays is reflected and can be used in X-ray reflectography. But most of the rays go through. With infrared, it's a little different. They go through the colors and then are reflected at the ground that is there. And if there's an underdrawing, you get the reflected light, and you can see that. The visual part, of course, this is the colors you would see here in the painting. And if you just use ultraviolet, is also interesting. Then this light is reflected on the first layer, which is normally the furnace layer. So you get the information whether this image was this painting was retouched or not. So there's also extra information on that. And using this information, where the people in art history did along, we just use these kind of things and port it to manuscript analysis, and you can see this works also there. To prove that it really works, so for instance, this is infrared reflectography. One colleague, Markus Diem, has done this kind of artwork here. This is drawn on the back, on the basis layer. As you see here, some kind of things, and afterwards he painted all kinds of colors onto the surface, and then the infrared reflectography shows you kind of very faint out these underdrawings that are there. And the idea is how to get it automatically done such that these kind of structures are highlighted, such that you can see what has been painted underneath. And you can use this also, of course, in manuscripts. How this works, we will see in a minute. Ultraviolet, as already mentioned, this is also quite heavily used in art analysis, but also in manuscript analysis, because you get also more information, and people like 100 years ago did sit in the library with a UV lamp on, and they try to see what is on the manuscript. However, this is not good for the manuscript, and it's also not good for the eyes. So you get kind of problems from this UV light, just like in Sun Studio, for instance, where it's the same problem. So further, you can have some fluorescence effects to even more see more what is there. However, we are more interested in the acquisition, and if we look at traditional RGB color cameras, then we see that there is no color measurement system in there. So what is measured there on these CCDs or CMOS is just intensity. And to get the color impression, there is a simple trick in all of the cameras. So most of the camera, except video cameras that have 3 chips, but usually traditional cameras have 1 chip, and they have some kind of filter in front of the sensors, and then you get the red and green and blue impression, and then you mix it together, and then you have some kind of reconstructed image because it's demosaicked from the raw image. And of course, you have only 50% of the green pixels available and only 1/4 of all blue pixels and 1/4 of all red pixels. So most of the color information is then just interpolated and is not really the color that is in there. But for our images, if we put it on Facebook or wherever, it doesn't really matter if the colors are correct. However, if you really would like to measure, it's necessary that you really measure the colors. And instead of measuring only 3 colors, multispectral imaging is now measuring more of them. So multispectral image like 10 or 15 or so, and not just only in the visible, but also in the infrared and ultraviolet part. That means you get some parts of the spectrum, and you can, for instance, see that if you have a multispectral image with some kind of filters or so, you can have this as a filter in the UV area, then in the near infrared between this one, and this would be the color filters that you could use in order to produce more than 3 channels, and you get more information than just the RGB. So traditionally, this would be blue, this would be green, and this would be red. So the traditional RGB camera would only have this one, and this one. However, here is more. And if you go in hyperspectral imaging, for instance, then you have even more. So the difference is only that you have even more of these color channels, where all the frequencies are really nicely separated from one another, up to a couple of hundred of them. So why does one do that, for instance, by the way? Well, this frequency gives you some information about the material that is reflected. So if you would like to know which kind of material or how much of what was in a color, you can use this kind of multispectral image or hyperspectral image, and then you find out which particles were there to make the color. And if you have these particles there identified, you can find out whether this painting, for instance, is a fake or not, because some colors were used at certain time periods, and if these ingredients are not there, then you can find out that this is not an original, for instance. So people are interested in this kind of analysis, especially not. Further on, so we go back to our 3 sensors, like RGB sensors in the eye, and we see if you have one spectrum, like for this one here, you have the spectrum, the blue one. This would be the spectrum that is like reflected from a certain color and measured in the imaging device. Then you get some specific color. And if you do a second spectrum, like here, the purple one, you see as a human exactly the same color. However, they have different spectra. So if you look carefully, you see in this part, for instance, if you look at the blue channel, a little bit blue here, turquoise, you have a value in the first spectrum that is here, and the other one is here. So you have different intensity values, even though you see the same color. And this is why people would like to have the frequency separated, because then you can really see which kind of material is there, because every material has a unique footprint as reflection of frequencies, and this is then measured in multispectral imaging. Now, how can we do multispectral images? Well, basically 2 ways. Either you use a camera with a filter, so there's, for instance, a filter wheel that is changing the filters in front of the camera, or you have an illumination that has the color that you would like to record in the camera, and you don't have any filters in front of the camera, so it's just intensities, and then you just do different colors that you project onto the surface, and then you will get the signal back. So both of them can be used, and multispectral images are then composed and either by a couple of filters or by different colors of the illumination. The better it is, the narrower the band is that you project onto the surface, the better it is for multispectral imaging, because then you can really separate the frequencies there. What is better? Well, it depends. In environments where you cannot control the illumination, like outdoors or remote sensing, you can only use the broadband illumination with some kind of filters. And of course, the filter change is mechanical, for instance. You can also use all others, but in principle, usually they are mechanical. And of course, you have a limited number of filters there, and you get some misalignments by the filters, because we will see the aberrations, the color aberrations will change the focus of the image. However, if you use this narrow band illuminations, you can only work indoors. So outdoors is not possible, so you have to have a dark environment, and then you can use your frequencies to be reflected by the surface. And of course, the good thing is you have no mechanical changes between the shots. You have fewer misalignments because it's one camera and just different light, and you're much faster. And of course, also there's less energy on the original. This is important in cultural heritage very often. So the shot is very short, and you have only limited energy on the surface. That's why people prefer the second way. And here, for instance, you see one of these acquisition systems we have here. There's a multispectral camera, phase one here, with some illumination devices. We have daylight LEDs and the LED panels with different colors. And then we have also a traditional camera for true color images, if you like. The other one has, of course, the chromatic camera has no filters at all. This filter wheel here, however, is here for doing UV images and UV reflectogram images. So there is some filter there because this cannot be done by the camera, but otherwise we do have no filter. And yeah, some linear unit that is moving the object from one camera to the next camera. So everything is automated, everything works with the control software, and here you see different spectra that we can have with our LEDs, and this is how it looks in reality. You see also here some diffusers, so that such that you get the image from the light from the LEDs more or less equal distributed onto the surface where you would like to take the images. And here you see the linear unit to move the object, and here are the two cameras. More or less, this was in the Sofia National Library in Bulgaria. This is in the Vatican, and here in the Austrian National Library. And here you see a darkening tent. Why? Because it's not possible to get a dark room at the Austrian National Library. So you have to bring your own tent in order to make the acquisition there. And of course, there's some computer there. Now, Now, most of the people do this kind of imaging, and that's fine. However, we find out that this chromatic aberration is a major problem, and people don't really care about this aberration. So what is the reason for that? Well, you have the refractive index of a wavelength of the ray here is wavelength dependent. It means that the angle is different in different colors. This is annoying in a lateral way. So instead of being in this part of the image, it's like here. So there's a displacement in the image of the pixels, which is annoying, but can be corrected in the post-processing, so you don't have to really care about. However, the longitudinal is really bad. Why? Because you have a loss of focus. And this is the main problem here, because the blue rays meet at this focal point, however, the red ones meet here. And if you don't care about these things, you get unsharp images, and most of the people do not care. So we did not find in the literature some information on who is caring about these kind of things, and that's why it all started. Now we have had a look on what happens, and found out that, of course, the conventional lenses are optimized for the visible spectrum. So you have some kind of here it would be sharp, and you have this simple lens that is more or less in this area from here to here. It's not so much deviation here. In principle, you would like if you have infrared and ultraviolet spectra, you have to have these kind of super achromat or apochromat lenses that stay more or less the same at all the frequencies. However, problem is this is not really true in reality, because not all the lenses are good, and not these corrections in the lens systems are quite complicated if you have only one lens system for all different bands, and this is what usually is in a camera. So if you have this multispectral camera, you have only one lens system, and this lens system should work for all different frequencies. And this, of course, doesn't really work. And as you see here as an example, so this would be nice. The blue frequency, you have nicely sharp images. If we switch to near infrared, for instance, the whole thing, that the center of the sharpness is a little bit changing upwards. If you go upper in the near infrared, it's even getting even more and more. And you see all of a sudden, if you take the image with your infrared area, everything is unsharp that was previously sharp. And usually you cannot really correct for that, because it's maybe too far away from, and it's getting even more and more unsharp. Even if you look, for instance, ultraviolet, you are almost at this point here. So you have to do something against this kind of thing. But actually, we found out that most of the people don't care about that. So you have unsharp images, and this is what we also did. We did have unsharp images, and we found out after a couple of years maybe that when we were working in the images, with the multispectral images, that they are still not sharp, and if they're not sharp, you cannot extract as much information as you would like to have. And that's why we try to get this kind of calibration done, because the only thing that differs is the distance. So you have to somehow calibrate the whole thing. And if you know the shift, as you have seen before, you can correct it either by moving the camera with a linear unit up and down, or you just have a motor focus and you adjust for that. So this is kind of measurement, and then you get this, by the way, this is some kind of tilted, so 45-degree tilted scale, and this would be the perfect sharpness that can be measured here or here, and this gives you then the amount of unsharpness that can be seen in the mirror. Well, you just measure it, so you measure the focus shift with this kind of device here, and afterwards you can have this kind of two-dimensional correction function for all these different wavelengths here, and this helps you to keep the acquisition in focus. And as already mentioned, you can either do the autofocus motor of the lens, or you just adjust the working distance. This is slightly faster here, and that's why we have chosen this one. However, there are also some, or other cameras have fixed lenses, and then of course you have to move the camera such that the distance is okay for everything. And if you, for instance, here, ultraviolet, do it in 1 meter distance. If you have no correction, everything is unsharp, of course, and if you do this correction, then you have the sharp images. So this was just one excursion into image acquisition, because most people in computer vision do not care about acquisition. So did we, but we found out that the results get much better if you get sharp images in each and every layer of the multispectral image. And the second part here is now, what can we do with these multispectral images? Well, we can look on the different channels, but this is not so nice. So if you look on your color images, you also don't look at the green, blue, and red channel. You just mix it, and then you see the image, and the same is here. So what we would like to have is combine all these kind of images such that we have one image that contains all the information, as you see here, maybe also in false color, that gives you the information that is necessary. The question is how it's done. So usually in the typical processing pipeline, we start with the calibration, as we have seen before. Then we do registration, because the single channels are not registered to one another. Then we do some kind of statistical analysis to reduce the dimensionality of the data. And afterwards, we do some kind of visualization. So this is the typical way, either visualization or analysis, to get the information that is really in the images. So first step is, what we would like to have is the reflective or fluorescent properties of the surface. Not just the nice images, but we would like to have spectral signatures, as said before. This can be used in order to find out which kind of ink, for instance, the manuscript it was. And usually it's done with X-ray reflectography. However, this is only a point measurement, and it's costly, and it's also not good for the material. And that's why our idea is to just use these multispectral images in order to find out also the different materials. And then it's only possible if you separate really the different frequencies there. So the measured intensities that we've seen before depend on the intensity of the illumination, of course, also distance and the angle of the illumination, and many, many more things. And only one of these many things is the properties of the surface imaged. So we have in principle to cover all the others such that we can get this frequency here. And this is kind of the problem of the whole thing. And yeah, as you see here, once again, you have this illumination source at a certain distance and at a certain angle, and this is reflected. And of course, also you have to somehow get this kind of function done such that you really get the frequency. So what's really interesting to us is the pure frequency here at this point. And of course, there's some kind of physical formula here where you have some part. So the intensity, the pixel intensity is a part of the light intensity that is coming to the sensor. Then, of course, also the attenuation that you have here on this pass here. Then you have the surface reflectance. So this is the part that we're really interested in. And then you have, of course, also an attenuation at the sensor. And what we're, as already mentioned, into this part here. So we have to really find out all the other ones that we get the surface reflectance at a certain point. And of course, the assumption is that it is a diffuse surface, because on specular surface, this really doesn't really work so good. Now, first thing, what is the problem in the real world is that you have some kind of uneven illumination, and even though you do some kind of diffusers and things, you have still the uneven illumination, and that's why you have to do some kind of flat field correction, such that you have the correction for all the points here at the surface. Sorry. This gives you then some kind of proper illumination there. Afterwards, we do the calibration. Not only for the distance, so the distance calibration is already done. Now here is the reflectance calibration. So we would like to know which kind of frequency is reflected how by a certain illumination device, and how much is there reflected. Because in cameras, you know that not all colors are acquired with the same intensity. So there is always the red part is always much higher than the blue part, so you have to correct for that. However, it's not only red and blue, but we start with the ultraviolet and end up with the infrared, and that's why the traditional color charts here do not really help. Why? Because you cannot find out, if you have different frequencies and different illuminations, what happens with the whole thing. That's why we introduce some kind of other things, namely here, these special targets with a constant reflectance in ultraviolet, in the visual and the infrared range, just to find out if you have different illumination frequencies, what happens with the intensity that is really covered by the camera. So this is more or less the calibration of different frequencies for all the different frequencies, such that you can correct for the intensities there. So this is the reflectance calibration. And as you see here, we have 2.5% reflectance, 50% and 99% reflectance. And what we would like to have is to get out just the frequency, but also these kind of parameters, like the intensity that's really covered by the camera, plus some kind of side effect that might come from stray light or fluorescence effects, such that we can correct all the different frequencies. And you see we have some kind of transfer functions that do this mapping from the measured values into the reflectance here, such that we can be sure that all the reflectance values that we have in our image are really the ones that we would like to have. And you see here, if you just do it with this chart here, you have these different intensities over the different wavelengths. So from 365 nanometers, everything is dark, so you would not have any possibility to find out what is what. Whereas here, these kind of targets stay the same for all the different frequencies. However, this gives you even the other information about the colors and in which wavelengths you are. So this is kind of the first step, and then you have to register the whole different layers. So you have like let's say like 20 different wavelengths, and then you have to correlate all the pixels more or less at the same place, or register all the same place, such that you get a vector of all the different frequency bands at one specific position. So this is a precondition for further processing. So if you would like to find out the spectral signatures of surface points, it doesn't really help if this point is moving all around in different images. That's why you have to really register them correctly to one another. And afterwards, you can do some visualization or analysis within these images in order to get the information that is covered there. So how is this usually, or what are the reasons for that? We have different imaging modalities, for instance, because if you have two cameras, you have to register the whole thing. The filters or the different colors, as we have seen, do make a difference, as the chromatic aberration. Also the objects. So since we are working with manuscripts, and if you illuminate manuscripts for a longer time, they start to move a little bit, and then again the different pixels are not on the same place anymore, and you have to correct for that, because otherwise the spectral signature of the point is not correct. And of course, also it's always the case in imaging that someone is doing unnoticed things, and then everything is no longer in line. That's why everyone starts with some kind of coarse alignment. Here you do some kind of sift feature analysis, and they do some kind of fine transformation. It's a quite easy part, so you just use a fine transformation, so you get some kind of coarse alignment. However, this is not enough, as already mentioned, because the paper might have moved in some parts and the other parts not, so you don't have a real parametric transformation that you can do that. So it's necessary to also have a fine alignment, and this is usually done with methods used in medical image registration, where you can really compute the deformation field and really do it for every pixel, such that you have an accurate registration of the different layers to one another. And we have looked into different algorithms and have just used one of these to get this registration done. Once all these things are registered, then you have to somehow find the information there. And a simple way of doing so would be to just take all the channels and put them together. However, what will happen is you just amplify the noise, and your signal is no longer there. And that's why you have to do some kind of compression, because these images are highly aligned, that there's a lot of things that are the same in all the channels. However, we are interested in the things that are not the same in all the channels. And that's why you have to somehow compress the whole thing, that you get the information that you would like to have, and you isolate the sources like the support, the inks, and the pigments. You're not interested in all the noise that is there. And the single images, of course, which has been done before, are very hard to interpret. So, but usually people in the humanities they just looked into single channels, and then they just reconstructed the whole thing with their eyes. So here we try to get this automatically done, such that you don't have to look at the different channels and find out what is changing there. And of course, you cannot see everything that is changing with your eyes, and that's why we just register them. And then you have really a spectral signature of every single point in the image. So it means how many of which frequencies are there. And as already mentioned, if you know something about inks, for instance, and you know their spectral signature, you can get this information out of this multispectral image. And this helps you to identify, for instance, the material. So how can we do now this compression? Well, there's lot of statistical knowledge there about PCA, ICA. You can do this with principal or independent component analysis and find out which components produce the interesting signal, for instance. However, you can also use supervised methods like classical machine learning, and here provide the algorithm with some example of classes, and then you get this kind of information back. Or you do linear discriminant analysis, for instance, or deep learning, to find out the information that is in the image there. So for instance, if you just use this like 12 images and you do some PCA here, you get these different components here. And if you look carefully, you will see, maybe this component and this component already has some information about what I would like to see. Not so much here, but here or here. So that means that there is some information in the different channels about the ink and about the background. So this is where it all starts. And if you work a little bit with PCA, you find out that it's not perfectly, because the axes are not. The axes are orthogonal. Maybe they should not be, because you only would be interested in the background and the foreground. You can use something like ICA. And again, you would like to separate the sources, and then with the ICA, for instance, is getting better. So these are, again, these kind of images, as you have seen before, in the different channels. And then you put everything together and get these two different inks that are on the surface, on the manuscript. For instance, you see here, this is a palimpsest, so there's two writings on the surface, and yeah, this helps you to find out both of these scripts here. However, this is not yet ready, of course, for scholars, because they don't see which one is which script. So you have to visualize them also accordingly, such that both of the scripts are readable, but this we will see afterwards. So like here, the independent components, you have, for instance, the component number 3, which is the overtext, and the component number 5 is the undertext. And you see some kind of separation is very nicely done here, so that if you're interested in the undertext, you just look at this component here, and if you're on the overtext, then you do this one. And if you, for instance, are interested in the shading of the surface here of the page, for instance, you can use another component. This is really nice. However, this is different to all manuscripts. So every manuscript is behaving differently. So this is a nice example where it works perfectly fine. However, this is not always the case, and that's why one has to think about how to get this thing done automatically. And this is usually complicated, because if every manuscript is different, you also have to train every manuscript, part of manuscript, such that you get the information that you would like to have. Still, we try to do that, having this kind of pairs where we have already this results, as you have seen before. So we have the input and the expected output, and then you can use all kinds of machine learning to get this thing done. So what you have to do, you have to annotate the foreground and the background, which can be done, for instance, with this independent component analysis. For one example, for instance, if you have your codices that have like hundreds of pages, then you do it for 1 or 2 or 3 pages, and afterwards it's learned, and then you can get this kind of differentiation between the foreground and the background, or between the foreground 1, which is the upper script, and the foreground 2, which is the lower script, and the background. So usually we don't have more than 3 classes, so sometimes 4, but this is very rarely the case. So usually only 2 or 4 or 3. You have to only do it on a small part, and then the rest of the remaining pixel. But this, however, doesn't really always work. So you just do some kind of separation in one page, then you get some kind of gun that is doing the work then for you, and is trying to get this information that is kept in the multispectral images automatically between the different bands. So if you're then ready, as we have seen before, you have 2 different scripts, for instance. However, the scholars don't want to have them separated for whatever reason, I don't know, but they don't want to have them separated. So you somehow have to visualize them not only separated, but also combined. And false color images, for instance, is one idea to do that. Or anything else. And here there's the comment from my colleague, this general more art and science, because this depends on the scholar, how he or she would like to see the results afterwards. Contrast enhancement is always a big topic. So usually people working with manuscripts or also with paintings are doing photoshopping all the time. And of course, they would like to also have some kind of contrast enhancement. And here we also have some method selected, because we did a lot of different tests like contrast limited adaptive histogram equalization, which gives you then more information in of the image. However, it's also more noise, but for an interface, people can play around and visualize things. And if you do the same thing also for paintings, you can have again different layers and get these fast color images in order to see more of them. However, yeah, we are more interested in manuscripts, as already said, and this is, for instance, the independent component number 1. So the first script, and this would be some kinds of outer parts here, and independent component 7 gives you the second text. So this is kind of other information. This is kind of not so nice, because both texts are over one another, and then you can separate. And if you really would like to see them, you just put them together in a false color image, and then you see both of the scripts, for instance. Yeah, this is the blue one here and the green one here. So this is what usually people would like to have. And we have some examples here. So scholars are usually pleased with these kind of images, because then they can read the whole thing, and that's more or less done. Also here, this part is not really visible. If you use this kind of technique, you can also read in this part. This is just UV fluorescence. You will see later on, if you use the combination, you will see much more. Here, palimpsest. So these are documents where 2 different scribes have written their text, and one was then erased afterwards before writing the second one. And you can make visible also the other ones that is behind. Also here you see, typically you have 2 different texts, and people are interested in both of them, and that's why you have to separate, and maybe also to make it really readable, because here you could see that there's something behind, but yeah, with this kind of technique it's better. Also here, doing this kind of combination, you see much more than you would see just looking at different channels, or just looking at different components of the analysis here. Now, this is nice for the scholars there, and they see something. However, what we are more interested in, and what we then use with this information, is typical document analysis. And here, one of these things you can do is write identification and retrieval. As you know, identification is the task of determining the author of a sample of handwritten set for writers. So you have a couple of samples of the writers, and you get some query, and you would like to find out who of these writers that you have in a database is the writer. So this is writer identification. However, if you would like to have just retrieve one document of a set of documents, then this is called writer retrieval. So you have a database, for instance, coming from an archive. So you have millions of pages, and then you would like to know whether there is a letter written by Einstein, for instance. You take one letter of Einstein, and then you find out, are there similar documents in the database that have also been written by Einstein. And this is really the case, because many of the archives don't know which material they have. Even if it's digitized, they don't know what is there. And this is one usual application in this area. So you just find out similar writings, for instance. Writer identification. The application in historic documents is the follow the trace of medieval scribes. So if you really can identifying the scribe, and sometimes you have some kind of initials of the scribe, then you also can find out whether a specific archives or digital library has another document of this scribe, because you already know how it works. Or of course, also for modern things, you can have a look on forensics. Has someone written a thread or whatever, or smart reading rooms and many other things. And like use case here for writer retrieval is again forensics, for instance, clustering of documents. This, for instance, is one example of the Stasi files we were working with. So this is real data from the Stasi files in Berlin. And the other question is whether one handwritten document is written by a specific person, because you don't know the person because they have nicknames, for instance, but you then still can cluster who has written what. So if you would like to work on that, then you have to have a look on what handwritings are. And here, for instance, this is one handwriting. So we made our own database with different handwritings. And what you find there is you have a text, and then people have to write a text. And this was one author, and you see that how the writing will change on one page only. So if you look carefully, you see this is the same author, and you as a human would not think that this line here and this line here have been written by the same author. And also here is the same author with two different scripts here, because this one has changed the pen. So this is maybe ink, and this is another pen, and then you see that the handwriting looks completely different. And also here, it's also another changing of the pen, and you see this is the blue one, and this is the black one. If you're not an expert, it's really hard to find out that these are written by the same person, because all of a sudden some characters do look different. And yeah, this is the main problem always in these handwritings. And yeah, it's more complicated with modern data than it is with historic data. Why? Because scribes in medieval times, for instance, were trained to really write nicely, and then you have printed there. However, you might think this is easier. However, then it's more complicated to find out which writer it was, because they all try to have this kind of really standard of writing, and they try to get all the individual shape of characters away. So there's a problem that is even more complicated in handwritings, and in historical handwritings, than it is in modern handwritings. So how did we start? We started, as already mentioned, with the Stasi files, where we applied some SIFT features, and yeah, we tried to compare the cluster centers of the training data and find out who is reading what. And as you see here, with two different writers, you might get two different histograms of these different patches here, and then you see that if you have this kind of distribution of the histogram, that is writer A, and if it's this, then it's writer B is at that time. So you see here in 2012, deep learning was not really at the place, and that's why we used it with traditional things, like with the feature space that you get with these different documents, and then you just cluster everything, and then you find out with a query document in which of these cluster it falls, and then you say, well, this is this or that writer. Well, so this is traditional writer recognition, and this performed, of course, and if you find it here, you find, well, this is the most similar histogram, and that's why it's this writer. However, we have an improper description of the feature space there, because the distance within the cluster and the distance to other clusters is disregarded, and that's why we try to use, as you see here, so one point here might belong maybe to another cluster, because for whatever reason, and because you don't have any distances to other cluster, this is not possible, and that's why we try to use the visual vectors then in 2013 and solve the problem for this application there. So how do we test if it really works? Because as you already heard, we worked with this Stasi files where we don't know who is who. We made up a dataset, a CBL dataset with 311 different writers, mostly students, and everyone had to write 5 pages, 4 in English and 1 in German. And this was the basis for these tests here. And of course, we generated the features for each document images, and then we try to rank them, however. And of course, if you would like to evaluate the whole thing with the nearest neighbor, for instance, you would like to, if you would like to identify the writer, then the top one has to be as the correct results. However, if you do it a little bit softer and say, well, if the result is in the first two results, then it's also fine. Then you have a little bit softer, or the results is in the top 5 or so, then you get a softer criterion. Why is this used? Yeah, because usually after the recognition, someone has to look onto the results and verify them. And if you have some kind of, as you have seen before, some kind of listed documents, a human operator can find out whether this thing is correct or not. And this helps to really find documents that are not really in the top 1, but show up in the first 5 or 7 documents. So at that time it worked quite nicely, and you see here we are, mostly we're quite good in this area. And then we use the whole thing for historical manuscripts, and we had 5 different megalithic manuscripts, and this is some kind of script that has been used from the 10th century until the 19th century in the Slavic world there. However, our data wasn't really nicely distributed because we had 7 different writers in 361 document images, but a real unequal distribution of writers. And you see here, for instance, the Glagolitic, which is a kind of interesting script because there's no words. There's just characters and there's no words. So every character is equally spaced. And that's why this script was not very distributed over Europe, and was exchanged to another font, the Cyrillic, because the Cyril has invented first this Glagolitic, and then he found out that it's not so nice, and afterwards this Cyrillic script also invented. However, in this church area, this Glagolitic was used for a long time, for instance. Great. Then we used these kind of images and tried out whether it's possible to get some results. However, we had to first pre-process the whole thing as text block segmentation, because you see these documents are kind of weird. So you have to find out where is the text. Especially if you're interested in this one here, you have to find out where is the text, and then you have to find out where are the lines, and then the next step is we have to find out where are the characters, and these characters are then usually binarized, and afterwards you can start with the recognition of the writer. And this already said the writers were not equally distributed, so we have one writer with 207 pages, whereas you have one writer that has only written 3 pages. So the distribution is somehow not balanced, let's say like this. And still, it was possible to get some quite good results in this area, because you see here, 95% in top 3 is quite good for this kind of thing. However, the data was limited, and of course, the next thing is also that, Glagolitic is a nice font because there is no words, and there's a large variation between writers in this case. What has been done afterwards, so not so much in the historic part, but we moved back to the modern scripts, and worked, of course, also further on writer identification. And here we have some application in the forensics. And again, you have different types of writings, like brain cursive ticker. You have writing utensils that have been used in different times, and so on. So these traditional problems with handwriting. And there are also some external influences like compulsion or other things, or internal influences like Parkinson's disease and emotional circumstances that change this kind of data. And the data, where it comes from, it's from prisoners. So it's forms that have been written by prisoners. So in Austria, if you go to prison, you have to write this kind of text that you see here. And this is then kept somewhere to identify if someone has written some text. And there is also like the standardized text, and that's all. They also have to write the CV here in this data set. This was also used, of course. And then along with these forms, you have 25 different forms over time, and yeah, you have to find out where's the text and things like that. So this is the easier way. However, then you have this handwritten resume. Of course, I cannot show any details here due to privacy reasons, but for everyone, you have just one of these forms that have been written plus a CV. So this is called the Write 1 dataset. And there is another dataset that is called Write 2. These are postal documents. So these are the threatening letters or postcards or envelopes that are sent to someone. And of course, the police would be interested if this kind of font can be found in the ones that have already been imprisoned. And that's why writer recognition is here of interest to the police agencies, for instance. However, it's not so easy because there's only a few lines of text, for instance, on an envelope, and yeah, it's not so easy to find out all the parts that you would like to have. Even more, there's all kinds of things that are sent to people, like these newspaper clippings or invoices or checks that you can use for these kind of things. If you are interested in fraud, for instance, then you have a couple of words there. And the first thing would be to find out in the database who has written that. So interestingly enough, in the beginning of this project, the data was not digitized. So neither the forms of the prisoners nor the other things here. So the traditional way is someone is sitting there looking at the thing that he has to analyze, like this one here, and is trying to find the matching candidate in some kind of analog database by looking through all the things and say, well, this might be the one that was imprisoned then and then there, so that the numbers that can be found in this database is quite low. So the dataset, Write 1, so they have to anonymize the dataset of 990 samples of 495 authors. And there's a second dataset of a collection from existing cases. And we have got 316 samples of 41 authors. So these are really cases that have been solved so that we know who is who in this data set, also from this one to that one. So you have this corresponding authorship of the different things here. And of course, there's also the text areas are all marked. So you some manual annotation to find out how it works. Again, this kind of different fonts from the same author. So this one time he was imprisoned, he has wrote in block letters, the other one in handwriting. Also here, like line font, so they have used some kind of help to write this thing here, because you see that they are all perfectly aligned, whereas if you write in block letters, this perfectly aligned is no longer available. So you have, again, this kind of interesting things in your data set. And the methodology that we used for this kind of application is the following. Of course, we have, again, the feature extraction with the SIFT, for instance, as you have seen before. Then we have these kind of image patches to use the feature descriptions and slant direction, things like that, and do some embedding in the network, try to get the aggregation done, feature vectors or whatever, and then find out a classifier with a similarity score. As before with the Stratifies, here we used for training the ICTA 2013 dataset. This is 100 scribes with 4 writing examples, to English and to Greek, for instance. And then we tried, for instance, first a batch extraction. The equalization is just by scaling, so that we have about the same size of all things on a batch, which is, for instance, the size of a letter. And if we use this kind of batch extraction on this data set, you see, well, quite nicely gets the batches here. If you do the same thing on our right data sets, that doesn't really give you the nice results. Why? Because there are lines in there. So sometimes there are lines and sometimes there are no lines. And if you do this kind of batch extraction with lines, then it doesn't really work. So people, we have to first get rid of the lines, and afterward it's working. Also here, baseline detection is also necessary here, of course, for these different lines. You see ICTAR on the left side and right on the right side. This works nicely, so we can use this, what we have already developed sometimes, and also some look onto the scaling. So you see the difference, for instance, between the ICTAR dataset and the right dataset is that the line spacing in the right dataset is much more differently. You see between 200 and 300, you have the most of them. This is not so the case in the ICTAR dataset, so you have to somehow adjust for all these kind of things. So here, for instance, batch extraction on the scale 1/6 of the images, you see it works quite nicely. And if you need to take 1/4, for instance, you get even more of these kind of batches there, which is fine for these kind of examples. As already said, for these examples where there are lines on it, it doesn't really work. So we have to integrate a pre-processing step to get rid of the lines, and then it would work. What we do first, approach a very naive one, as the name says, local naive based nearest neighbor approach in order to find this kind of sorting. This is because we were already having this from previous things, and we found out that it works. It works, as you see here. But it has to have some room for improvement. That's not like this. So this would be the results for that. So this is the query on the left, and then you see the things that we found. And for a human, so if you don't know the ground truth, it's very complicated to really find out whether the correct thing is in the whole thing or not. And that's why you have to have ground truth. But here, for instance, if we look at the results, it's the mean average precision is about 40% with SIF features, and fast features 37, even lower. So there are results, but it doesn't really work to solve problems. That's why, of course, what we can do, go into the area of machine learning, and we try to use the features embedding, as we already said, that we have the batches and from SIF positions, and try to get this information such that we can find out the writers. We used here, for instance, the vector of locally aggregated descriptors and net relate for and generalized max pooling for the aggregation, and neural network attention-based transformers and graph neural networks, just to try it out. And as you see here, interestingly, it works nice on the ICTA dataset. However, on the real datasets that you see here on these CDs and writing, it's not so good. So the previous version was much better. However, on the second part, like on the newspapers and things, that was working quite better. So we're now back on the work on writer recognition and trying to get it on the real data. And of course, we could use this kind of information that we gain here on our historical data as well. But the question is where to get this kind of nicely annotated images from. And we try to find it also as a data set that we can use within the Austrian National Library in order to find out whether it works also for these kind of applications. To conclude, we have a look on multispectral imaging in this talk, why this is important and why it should be preferred for all cultural heritage objects. So this is, from my point of view, really important, because not only on writings, you can use whatever, like statues, like whatever you would like to have. There is always more information if you use multispectral imaging, and of course also you can, up to a certain degree, also find out the material. Chromatic aberration have to be concerned, of course, because they have an impact, and we didn't find any publication where this aberration have been taken into account, because usually there is no multispectral image analysis afterwards, and of course this kind of data can afterwards be used for getting more and better information there. Then you've seen some writer identification and writer retrieval methods, and we started with the Stasi files and are back in the forensic business again, and had some excursion to the historic documents. However, we also have one new project that we already had written an application for, that is also again concerned with this historic document and writer recognition there. And maybe the most interesting thing for this application in historic field is that we do not have explicit modeling of the graphical styles, so no graphemes, and the research done in this area has always been based on graphemes. And if you look onto modern script identifiers, they also always get on these graphemes, and maybe this could help to get away from the graphemes word to a modeling of the whole thing with image descriptors. And as you've seen in real world application, of course, you have to really adapt to the data. And we are now, well, in half of the project, and we will still work further on this problem. So, of course, this work was not done by me, but mostly by my colleagues, Simon Brenner, Markus Diem, Stefan Viel, Fabian Hollas, Florian Kleber, Marco Beer, and many more, which I would like to thank. And of course, I would also like to thank you for your attention. And yeah, this would conclude my presentation.
Well, thank you very much for this presentation, and I do have some applause for you. I hope you can hear it.
Yeah, I hear it.
Excellent.
Yeah.
Great, wonderful presentation. In particular, the first part on the hyperspectral imaging. I think this is something that essentially everybody working in the field and image processing is struggling with, and the solutions that you suggested, they are really very, very good. And I think everybody working in this should have a look at your presentation. I'm really impressed how you managed to calibrate all of this. I know that we had a lot of trouble with hyperspectral imaging and the chromatic aberrations and also geometric instabilities and so on. And this is really great work. I'm yeah, very impressed how you managed to do that. And
thank you, because we were working for that on 10 years maybe. So
yeah, it's
in the beginning we didn't really care about all these kind of different parameters, and then found out that this is really necessary, because you don't find much literature describing how to do that.
Yeah. Yeah, also, of course, your work on the writer identification is also really impressive, and I think you're driving the state of the art quite a bit with your work. So also great. So given all these observations, you had these wonderful images that you've shown. So this is really impressive. Is there any new insights that came out of your image processing that you know of, that they historical discoveries? And
this was heavily used in the humanities, and they found out a couple of things, because we increased on some documents, we increased the readability to up to 90%, so they could read 90% more than it was before. And this, of course, gave was a huge impact in this humanities, because then you can read things that have not been read before, and you can also attribute documents to a certain writer, because you see things that have been erased afterwards. But this is very often the case. Someone has written something, and then after 100 years, someone didn't like this guy and have erased the signature on all the pages. And afterwards, you can use this to get the signature back, for instance. So this was also, for instance, the case, and one of the most important documents in the library in Innsbruck. I forgot the name, and then they found out who has really written the thing, and that this was really original, and it was from whoever that was important. So people are libraries and other people frequently show up at our institute, and we do then the image acquisition, and then we produce these images for them. So we do it quite frequently. Yesterday, the colleague Simon Brenner, who does most of this multispectral work, was in the library in Graz, in the university library in Graz, in order to acquire a couple of documents and also maybe do some consulting if they would like to buy one of these cameras. It's not so cheap, but if you have a lot of, because this is what I always tell the people also in archives, please do all the acquisition, not only with your RGB Nikon cameras, but with multispectral cameras, because there's much more in the documents that you can see with your naked eye. And many of the documents, like in the Austrian National Library, are palimpsests. No one knows that, but they have been rewritten, and no one is really taking care about that.
So what's the future of digitization? Will it be always hyperspectral?
Yes. Yes, I think if you would really like to have the cultural heritage documented in a correct way, you have to do it hyperspectral way, because it's just an image is not enough. And all the images that are taken, for instance, in the art museums, are usually not corrected. So they don't use calibrated cameras. So they have the color things down there, the color charts there to have this color correction afterwards, but the geometric correction is not done. So no one does this. This is really interesting. And if you see that, if they have this kind of different, if they have huge paintings, if they have to somehow stitch the whole thing. And then you see that these images do not really fit, because you have these distortions of the camera, and they don't care about the distortions of the camera. Very frequently seen, so that people that work with documentation in archives and in libraries and in museums, they don't really care about what is then done with the digital data. So they are mostly photographers. So they are trained photographers, and they're not digital photographers. They're just photographers. That's what they can really good is produce a perfect image for humans. But for analysis, it's a different way. So,
but doesn't it imply that, I mean, you advanced the state of the art quite a bit in terms of digitization. Can we ever be done with digitization? Because every time we have a new sensor, a new insight on how to make it better, we have to go back to the original paper, right?
Yeah, it is. So if you look at this, because these kind of technologies have mostly been used in art documentation, because there's a huge market. So if you would like to know whether you have a real Rembrandt or not, this makes a difference. And that's why there were a lot of money there, and the people have always tried to get all kinds of information about this painting with multispectral imaging and so forth. And there, of course, every 10 years or so, the whole paintings are re-digitized, because there's new insights there and new here and there. So every time they go for a painting, it's re-digitized. And I guess this will be also with archives. For instance, the Austrian National Library was digitized by Google, and like 5 or 10 years ago, I don't know, that I do not remember. However, nowadays you will do it differently. So in principle, you would have to do the same thing once again, because with the knowledge of today, you would do the digitization differently. And this will always happen. So if we now have a perfect method for acquiring whatsoever, 20 years later, you say, well, this is nice, but you should do it differently. Especially, for instance, in this manuscript area. So what they have done there, because they always knew that there is there might be some writing beneath the original writing. Mm-hmm. They did use some chemicals, put it on a manuscript, then this thing was readable for, let's say, 1 or 2 hours, and then the complete manuscript was destroyed forever. So this was done like 100 years ago. So this was the first way, but people found out that this is not the right way, because you completely destroy the original. And afterwards, as soon as someone is working with this material, the probability that it's destroyed is very high. Why? Because in the former days, they used really high power UV lamps. this energy is much too high for the documents, so they destroyed the contrast, or infrared. So they had the more the better. Of course, it's not good for the originals. Nowadays, people are more concerned about that, and that's why.
Yeah, so when we're speaking with museums and archives, they often consider digitization as something that has to be done, and then it's done. It's sometimes very difficult to tell them, look, you digitize it now, but in a couple of years, we would probably do it in a different way. So did you encounter such discussions?
Yeah, sure. Yeah. But if you go to museums, they know that this will happen, because if they look at the material and if they would like to print it now digitally, they find out that the material is not correct and they have to rescan everything. And they now get the idea that this might be a good idea of do it every 10 years or so, every 20 years. But the main problem is that most of the content of archives is not digitized yet. So it's only 10% or so of all the things that are there are digitized. So maybe it's a good idea to start to try to get the digitization of everything and then to digitize, because
But we probably need something like scan robots, right? In order to
So Fraunhofer in Darmstadt has this scan for 3D scanning, so a complete thing here. But they never sold anything about this. So it's a prototype that was never bought by any of the museums. This is complicated, because museum is a different world, or archives is a completely different world. So they have different views on everything. But sooner or later, there will be younger people there, and as we see here in Austria, the new heads of these institutions here, they are younger and they have some idea that it's necessary to digitize everything, and that this is a good way now, because the old that are now going to retire, they always said, well, we didn't need that for the last 40 years, why should we need it in the future? But the new ones that are then coming, that they are interested in these kind of things, and at least in Austria, we have archives like Haushof and Staatsarchiv that has now a new director that is also interested to get everything digitized. But again, then the problem is they do it internally, and they don't care about what has been already done by others. And then you find out, well, nice data, but you should have done it differently. I find it all the time, because, for instance, there is a photo archive somewhere, and they made nice visualization of all these kind of photos they had, but only the front side. And there's always some information on the back side. And so you don't have any information now, who was the photographer, when was it photographed, anything else, because they just made the photos and they digitized the photos, and they did not scan the backside, because they said, well, there's some information there, we can always look at it if you like. But who would have a digital archive and then say, well, I have to go there to find out who has done what? And I say, well, you should maybe also scan the backside, because this is where the information is on.
Absolutely.
The ones who are scanning it, they don't think about that. Why should we take the backside? There is no photo on it.
So, given your works in writer identification, and you've been working, for example, with the Stasi files and so on, are there any additional insights that you could create with the methods? What did they found out?
Yeah, the Stasi project was stopped on political reasons, because the ones that would be found in this data set were not very, very pleased that these things are developed, so they stopped everything. So there is no longer a writer identification, because the probability that they will find things that someone would not like to have found is very high. So they stopped it. But for this kind of other thing, as a other writer recognition, this is used by different people. For instance, in police or in forensics, there are people working on that. We are not the only one, but the question is how it can help. And the only thing is, we have a long collaboration with this federal police, The only thing or the only way to do so is just having a tool for there. So what they do is they have this huge database, and then they have some query, then they get like 50 results, and then they select manually which ones are the most interesting ones, and then they do the manual way afterwards, because this otherwise it's not allowed to go to the court. If you do just say, well, you cannot go there, so the computer said that this is the author. So this not really well. So this is just a tool for them to get a lower search base.
I see. Yeah, I just wanted to ask what your forensic experts are thinking about deep learning methods and their how you can interpret them.
Well, we have it completely outside. So it's just a pre-step to find the ones that they will never find manually. So they are fine with that. First, because we work with them for like 10 years now. Firstly, the ones that are doing the work, we're always telling, well, we don't need it because we know what we do and we don't need these things. But then they found out that it really helps. And I said, well, this helps me working, so I can find my things much faster, so I have more time for coffee and other things. So they introduced now the systems that we developed for other things, like for tool marks and for shoe prints. They implemented it now all over Austria, such that they have some kind of tool that can help them find data in a huge pile of data. So they're not interested in machine learning or something else, but it's just for the expert that he gets or she gets the examples, and then they do it the manual way as they always did.
When you do all this pre-selection, is there a risk of introducing bias by you?
Yeah, yes, of course. There is, as always, there's a huge risk of bias there, because we use the original data there, and this data is biased by the one who's working with the data. And of course, also, if you do this with these footprints, for instance, again, it's biased by the one who's using these footprint things, because some people say, well, this method A is the best to get the footprint, and then the other ones say, no, it's method B or so, and then you get a complete mess. That's why we also have, first thing that we did with footprints, for instance, we were also making an own database where we had standardized 100 people and with different shoes walking on a so-called shoe street, where there are 10 different ways of getting this imprint of the shoe, and so that the bias is no longer there. Because if you use real data from the police, this is a complete mess. Depends on who works with the material.
Absolutely.
It's the same as with the writer recognition, because there's one or two people there at federal police doing this task, and they of course have their way of doing that, and they think this is the only way how one could do that. So this is always complicated to show them that it's not replacing them, because this is the first fear, because we could be replaced, but it's helping them. And then we should this first examples, the one that was very skeptic was say, well, it seems that you really find things that are in the data, which was previously not so easy. So this is a long way to go, but the longer they work with this system, and there's a company behind it doing all this kind of user interface and things, the longer they work with the system, the more they have ideas where we could use it additionally. So this started with one project, and now we are in writer recognition. That's sure that in 2 years, someone will show up and say, well, we would need this for whatever. Again, because if it works in this area, why shouldn't it work in the other area? And then you're all of a sudden in a completely different field, because tool marks and shoe prints and writers are completely different things in principle. You can use the same user interface, but this is more or less it.
You have to train from scratch and need all the annotated data.
Yeah, you have to need the annotated data, and try to get a bias, and then most of the images they have are not good, because sometimes they use it this way or another way. Yeah, you have to train the ones that are taking the images or taking the data. Do it all at the same time, because otherwise it doesn't work. And this is very complicated with police, because they are public servants, and complicated to work with. Because we were thinking that these systems already exist, because if you look this kind of TV
and CSI
things, but everything is there, but in reality nothing is there. We were really impressed that the only thing they had was fingerprints. Everything else is not there.
Wow.
So no computer whatsoever in Austria, and I learned that this is the same in all the different countries. So in Germany, there's also no system for footprints, for instance. Yeah, really interesting. No one works in this area, also worldwide. So there's a couple of people working, but there is no one who's really providing a product for police, for instance. Not there.
Amazing.
For fingerprints, a lot. For the rest, nothing.
Oh, and other biometrics like face detection and so on. I think there's
face detection is there, yeah, of course, because there's a lot of companies that sell these kind of things. That's there, of course. But any other forensic, not there, because the market is so small. So who is interested in tool marks? Who is interested in footprints? No one.
Mm-hmm.
Face is a different story.
It's probably also difficult to get the data because there's maybe not so many applications or cases.
For footprints, so for instance, the footprint is much more important than fingerprints on crime scenes.
Oh,
because most of these criminal people, they have gloves, because if you're a criminal, you have gloves. So there are no fingerprints on a crime scene. So this is just for the ones that are not doing it regularly. However, what most of them forget is to change their shoes and to throw away their shoes, because every shoe print is individual for every person. So your shoes have a specific pattern. It's only your shoe has this pattern. And that's why you can identify people by shoes. So this is the first thing that police does. If you have a suspect, they go home to his home and take away all the shoes that are there, because this is the real thing that you can identify people. It's not about fingerprints, because or if you bank robbery, if you rob a bank, most of the people change their clothes and have gloves, everything, but they always have the same shoes. This is where policemen look first, which kind of shoes. That's why it's so important.
Very interesting.
You learn a lot in this field.
Well, it's good that people don't know about this. So because otherwise they would try to fake their shoe prints and so on.
Yeah, the first thing they have to change their shoes and throw them away, such that they cannot be found.
Good to know. Robert, this was a fantastic presentation. I really enjoyed the discussion afterwards. It was really awesome to have had you here, and I'm very glad that you accepted the invitation. So I have another round of applause for you. Okay, you've just seen the exciting talk by Robert, and I think there were many different things that came up in the discussions. And of course, if you've seen anything you have further interest in, Robert is of course available, and you can ask questions to me or Robert either by email or just using the comments function under this video. And we would be very glad if you ask any questions, if you want to see any research papers, if we can point you to literature. I think this was a lot of magnificent work, and if you're interested, just contact us. And if you like this video, then leave a like, and of course wait for the next episode of Beyond.